Hi, my name is Basir. In this video, I'll be teaching you about valence bond theory, hybridization from chapter 8, chemical bonding, class 10, Telangana state syllabus. In order to understand hybridization, let us consider the formation of beryllium chloride molecule. We know that the atomic number of beryllium is 4 and the electronic configuration is 1s2, 2s2. From the electronic configuration, we see that the first two electrons are getting paired in the 1s orbital. The next two electrons are getting paired in the 2s orbital. Let me show you this in the form of a box diagram here. So the first two electrons of beryllium, they get paired in the 1s orbital. The next two electrons of beryllium, they get paired in the 2s orbital. Beryllium does not seem to have any unpaired electrons, and since it does not have any unpaired electrons, it is not expected to form any covalent bonds. But beryllium is forming two covalent bonds. Beryllium is able to combine with two chlorine atoms. How is it possible? This is what really happens. One of the electron from the 2s orbital, it jumps to the 2px orbital. And when that happens, beryllium now have two unpaired electrons. And since beryllium has two unpaired electrons, it can very well form two covalent bonds. Since beryllium is combining with chlorine, let us see the electronic configuration of chlorine also. The atomic number of chlorine is 17. From the electronic configuration of chlorine, we see that chlorine has one unpaired electron in the 3pz orbital. Let us see the same information in the form of a box diagram here. So chlorine with the atomic number 17, it has one unpaired electron in the 3pz orbital. This is what really happens. Beryllium is forming two BeCl bonds. Beryllium is able to combine with two chlorine atoms. The first bond is formed when the 2s orbital of beryllium containing the unpaired electron, it overlaps with the 3pz orbital of the first chlorine atom. The second beryllium chloride bond is formed when the 2px orbital of beryllium, it overlaps with the 3pz orbital of the second chlorine atom. I have written this information in the form of a diagram here. Since the S subshell is spherical in shape, I have drawn a sphere here. And since the P subshell is dumbbell in shape, I have drawn a dumbbell here. So the first bond is formed when the 2s orbital of beryllium overlaps with the 3pz orbital of chlorine. When the 2s orbital of beryllium overlaps with the 3pz orbital of chlorine. The second bond is formed when the 2px orbital of beryllium, it overlaps with the 3pz orbital of chlorine. Now, if you see very carefully, you get to see that the overlapping orbitals are different. During the formation of first beryllium chloride bond, the overlapping orbitals are 2s and 3pz. During the second beryllium chloride bond formation, the overlapping orbitals are 2px and 3pz. Since the overlapping orbitals are different, the bond strengths of two beryllium chloride bonds must be different. But it is practically proved that the two beryllium chloride bonds that beryllium forms have the same bond length and the same bond strength. How is it possible? This is where hybridization comes into picture. This is what really happens. 2s orbital and the 2px orbital, they intermix. They intermix and they form two hybrid orbitals. Why two hybrid orbitals? Because two orbitals are intermixing, will get two hybrid orbitals. And what will be the name of those hybrid orbitals? We get the name of the hybrid orbitals from the orbitals that are intermixing. So the s orbital and the p orbital, they are intermixing. So we get sp hybrid orbitals. So we get two sp hybrid orbitals. So thus 2s is no longer 2s, it becomes a sp hybrid orbital, and this 2px is no longer 2px, it becomes sp hybrid orbital. So now if you see, the overlapping orbitals are same. The first beryllium chloride bond is being formed when the sp hybrid orbital is overlapping with 3pz orbital of chlorine. The second beryllium chloride bond is formed when the sp hybrid orbital of beryllium is overlapping with the 3pz orbital of the second chlorine atom. So the overlapping orbitals are same now, and so beryllium chloride bond length and bond strength will be obviously same. So this was an example of sp hybridization. We'll learn about sp2 hybridization, we'll learn about sp3 hybridization also. Once again, we get the name of the hybrid orbitals from the orbitals that are intermixing. Since here s and p orbitals are intermixing, we get the name sp hybrid orbital. Right? Let me read out the definition of hybridization for you. Hybridization is a phenomenon of intermixing of atomic orbitals of almost equal energy which are present in the outer shells of the atom, and their reshuffling or redistribution into the same number of orbitals but with equal properties like energy and shape. Let's see it here. So we saw that the 2s orbital and the 2px orbital, they are intermixing. Please remember, 2s and the 2px orbital, they are in the same orbit. This 2 that you see here, it is nothing but the principal quantum number which is used to denote the orbit. So both of these orbitals are in the second orbit. Since they are in the same orbit, the energy difference between them is not too high. They don't have the same energy, but the energy difference is not that high. So these two orbitals which are in the outermost orbit, we can see here that beryllium has two orbits, the first orbit and the second orbit. Second orbit is the outermost orbit. So the two orbitals in the outermost orbit, they will intermix, and once they intermix, how many hybrid orbitals we will get? Since two orbitals are intermixing, we'll get two hybrid orbitals, and those hybrid orbitals will have the same bond length and the same energy. So now in beryllium chloride molecule formation, the sp hybrid orbital is overlapping with the p orbital of the first chlorine atom. So a sigma bond is formed between sp and p. Sp hybrid orbital of beryllium is overlapping with the p orbital of chlorine, and it forms a sigma bond because they are overlapping end to end. And then again, the sp hybrid orbital of beryllium, it overlaps with the p orbital of the second chlorine atom end to end, and it again gives us a sigma bond. So beryllium forms two bonds with the two chlorine atoms. So beryllium is able to form two covalent bonds, and those two covalent bonds must be separated at an angle of 180 degrees. The shape of beryllium chloride molecule is linear. The bond angle is 180 degrees. From the valence shell electron pair repulsion theory, we saw that if the central atom has two covalent bonds, and if it does not have any a lone pair of electron, then the bond angle has to be 180 degrees and the shape should be linear. Let us now consider the formation of boron trifluoride molecule. The atomic number of boron is 5 and the electronic configuration is 1s2, 2s2, 2px1. From the electronic configuration, we see that boron has one unpaired electron in the 2px orbital. And since boron has only one unpaired electron, it is expected to form only one covalent bond. But boron is able to combine with 3 fluorine atoms and form boron trifluoride molecule. How is it possible? Since boron has only one unpaired electron, it is expected to form only one covalent bond, but boron is able to combine with 3 fluorine atoms and form a boron trifluoride molecule. How is it possible? This is what really happens. Again, one of the electron from the 2s orbital, it jumps to the 2py orbital, and once that happens, boron trifluoride now has 3 unpaired electrons, and since it has 3 unpaired electrons, it can very well form 3 covalent bonds, right? Since boron is combining with fluorine, let us also see the electronic configuration of fluorine. The atomic number of fluorine is 9 and the electronic configuration is 1s2, 2s2, 2px2, 2py2, 2pz1. From the electronic configuration, we see that fluorine has one unpaired electron in the 2pz orbital. So the first bond should be formed when the 2s orbital of boron overlaps with the 2pz orbital of the first fluorine atom. The second bond should be formed when the 2px orbital of boron overlaps with the 2pz orbital of the second fluorine atom. And the third bond obviously should be formed when the 2py orbital of boron, it overlaps with the 2pz orbital of the third fluorine atom. But if that happens, you can see that the overlapping orbitals are different. Boron does not have the same orbitals here. It has s orbital here, it has px orbital here, it has py orbital here. These two orbitals px and py are identical. We call them as degenerate orbitals. Remember, p has three degenerate orbitals, px, py, pz, three degenerate orbitals, and they have same energy. So we don't have a problem with px and py, they are identical, but this is s. So you have a s orbital and then you have p orbitals, different orbitals that are overlapping with the 2pz orbital of the three fluorine atoms. When the overlapping orbitals are different, it is evident that the bond strength and the bond length should be different, right? Again, here also hybridization takes place. The 2s orbital and 2px, 2py orbitals, they intermix, and when they intermix, we get three hybrid orbitals. Why three hybrid orbitals? Because three orbitals are intermixing, we get three hybrid orbitals. And what should be the name of those hybrid orbitals? We get the names of the hybrid orbitals from the orbitals that are intermixing. So we have a s orbital here, and then we have 1, 2. How many p orbitals? 2 p orbitals. So the name of our hybrid orbitals will be sp2. And we get how many sp2 hybrid orbitals? We get 3 sp2 hybrid orbitals. Because 3 orbitals are overlapping, we'll be getting 3 sp2 hybrid orbitals. So this 2s is no longer 2s, it becomes a sp2 hybrid orbital. This becomes a sp2 hybrid orbital. This becomes a sp2 hybrid orbital. Let me just cancel this out and let me write sp2 in place of 2s, 2px, 2py. So this is what it should really look like. Instead of 2s, I'm going to write sp2. This also becomes a sp2 hybrid orbital. This also becomes a sp2 hybrid orbital. Since 3 orbitals were intermixing, we get 3 hybrid orbitals. And what will be the name of those hybrid orbitals? Again, it depends on what orbitals are intermixing. We have one s orbital which is intermixing, and then p orbitals. How many? 2 p orbitals. So we get 1s and 2 p orbitals that are intermixing. So we get sp2 hybrid orbitals, right? Now it is pretty simple. Now sp2 hybrid orbital of boron, it overlaps with the 2pz orbital of the first fluorine atom. Again, sp2 hybrid orbital of boron, the second sp2 hybrid orbital of boron, it overlaps with the 2pz orbital of the second fluorine atom. The third sp2 hybrid orbital of boron, it overlaps with the 2pz orbital of third fluorine atom. Now sp2 hybrid orbital of boron is combining with 2pz orbital of first fluorine atom. The second sp2 hybrid orbital is combining with the 2pz orbital of the second fluorine atom. The third sp2 hybrid orbital is overlapping with the 2pz orbital of the third fluorine atom. Now the overlapping orbitals are same, and since the overlapping orbitals are same, the bond length and the bond energy will obviously be same. You can see the same information here in this diagram. We have boron as the central atom. Again, a central atom is an atom to which all the other atoms are connected through covalent bonds. So boron is the central atom here. It is forming 3 covalent bonds with the 3 fluorine atoms, and as per the VSCPR theory, the valence shell electron pair repulsion theory, the bond angle has to be 120 degrees. Let us now consider the formation of ammonia molecule. From the chemical formula of ammonia, we see that it has 1 nitrogen atom and 3 hydrogen atoms. It ideally means that 1 nitrogen atom is combining with 3 hydrogen atoms. Let us see the electronic configuration of nitrogen. The atomic number of nitrogen is 7. The electronic configuration is 1s2, 2s2, 2px1, 2py1, 2pz1. From the electronic configuration, we can make out that nitrogen has one unpaired electron in the 2px orbital, one unpaired electron in 2py orbital, one unpaired electron in 2pz orbital. Since nitrogen is combining with hydrogen, let us write down the electronic configuration of hydrogen also. The atomic number of hydrogen is 1, electronic configuration is 1s1. So hydrogen has one unpaired electron in the 1s orbital. From the valence bond theory, we know that when two atoms come close to each other, the outermost orbitals having unpaired electrons, they should overlap. So 2px orbital of nitrogen, it should overlap with the 1s orbital of the first hydrogen atom. The 2py orbital of nitrogen should overlap with the 1s orbital of the second hydrogen atom. The 2pz orbital of nitrogen should overlap with the 1s orbital of the third nitrogen atom. Since nitrogen has 3 unpaired electrons, it can very well form 3 covalent bonds. But we have a problem here. Let me draw the axis here, the x-axis, the y-axis, the z-axis to you, just so you can be a bit clear about the problem that we will encounter. This is the x-axis, this is the y-axis, this is the z-axis. We know that the shape of the p subshell is dumbbell. So I have drawn a dumbbell along the x-axis, along the y-axis, and along the z-axis. I thought this will be a good way to explain you the axis. Let us consider, if we consider this as the x-axis, this as the y-axis, and this as the z-axis, you get to see that the x-axis and the z-axis are perpendicular to each other, meaning they make 90-degree angle. In the same way, the y-axis and the z-axis, they are perpendicular to each other, they make 90-degree angle. And again, x-axis and y-axis, they are perpendicular to each other, they make 90-degree angle. So remember, the x-axis, the y-axis, and the z-axis, they are mutually perpendicular to each other, meaning they make 90-degree angle with each other. Now, I cannot draw a three-dimensional diagram here on a piece of paper, but this is what it is. So this is the x-axis, this is the y-axis, this is the z-axis. So if the 2px orbital overlaps with the 1s orbital of hydrogen, this is what should really happens. The s orbital is spherical in shape, so I'm drawing a sphere here. So the 2px orbital of nitrogen, it is overlapping with the 1s orbital of hydrogen. And again, 2py orbital also overlaps with 1s orbital of the second hydrogen atom. Again, 2pz orbital of nitrogen, it overlaps with the 1s orbital of the third hydrogen atom. But if this happens, since the x-axis, the y-axis, and the z-axis are mutually perpendicular to each other, the bond angle has to be 90 degrees, right? The bond angle has to be 90 degrees because the x-axis and the y-axis, they are mutually perpendicular to each other. The bond angle has to be 90 degrees. But from the valence shell electron pair repulsion theory, we saw that if the central atom has 3 covalent bonds and if it has a lone pair electron is that pair of electron which is not involved in bonding. So from the valence shell electron pair repulsion theory, we already read that if the central atom has 3 covalent bonds and 1 lone pair of electron, then the bond angle should be 107 degrees 48 minutes. But here if we go through this procedure, we see that the bond angle is 90 degree. But as per the VSCPR theory, it is proved that the bond angle has to be 107 degrees 48 minutes and not 90 degrees. So again, here also hybridization takes place. This is what really happens. 2s orbital, 2px orbital, 2py orbital, 2pz orbital. So these 4 orbitals, they intermix. Since 4 orbitals are intermixing, we get 4 hybrid orbitals. And what should be the name of those hybrid orbitals? I told you time and again that the name of the hybrid orbitals will be taken from the orbitals that are intermixing. Let us see here. So we have a s orbital and then we have p orbitals. How many p orbitals we have? 1, 2, 3. 3 p orbitals that are intermixing. So the name of the hybrid orbitals will be sp3. And how many sp3 hybrid orbitals we get? We get 4 sp3 hybrid orbitals, because 4 orbitals are intermixing. We get 4 sp3 hybrid orbitals. So let me write this down for you. So this is 1s. This 2s becomes the sp3 hybrid orbital. This 2px becomes a sp3 hybrid orbital. This also becomes a sp3 hybrid orbital. This also becomes a sp3 hybrid orbital. Right. So since these 4 orbitals were intermixing, we get 4 hybrid orbitals. And what should be the name of those hybrid orbitals? We get the name of the hybrid orbital from the orbitals that are intermixing. The s orbital and 1, 2, 3, 3p orbitals were intermixing. So the name of the hybrid orbitals will be sp3. This becomes a sp3 hybrid orbital. This becomes a sp3 hybrid orbital. 2py becomes a sp3 hybrid orbital. 2pz also becomes a sp3 hybrid orbital. Now the overlapping orbitals will be same. One of the sp3 hybrid orbitals is getting 2 electrons, while the remaining 3 sp3 hybrid orbitals are getting 1 electron each. So this sp3 hybrid orbital of nitrogen, it overlaps with the s orbital, the 1s orbital of hydrogen, the first hydrogen. And again, this sp3 hybrid orbital of nitrogen, it overlaps with the 1s orbital of the second hydrogen atom, and this sp3 hybrid orbital which has an unpaired electron, it overlaps with the 1s orbital of the third hydrogen atoms. Now if you see, the overlapping orbitals are same, so the bond strength and the bond length is same, and we get the bond angle as 107 degrees 48 minutes. Let us now consider the formation of water molecule. We know that the chemical formula of water is H2O. So 2 hydrogen atoms and 1 oxygen atom. Let us see the electronic configuration of hydrogen and oxygen. Atomic number of hydrogen is 1, electronic configuration is 1s1, which means that it has 1 unpaired electron in the 1s orbital. The atomic number of oxygen is 8 and the electronic configuration is 1s2, 2s2, 2px2, 2py2, 2py1, 2pz1. From the electronic configuration of oxygen, we can see that oxygen has 1 unpaired electron in 2py orbital and 1 unpaired electron in 2pz orbital. And as per the valence bond theory, when 2 atoms come close to each other, the orbitals having the unpaired electrons should overlap. So the 2py orbital should overlap with the 1s orbital of the first hydrogen atom, and 2pz orbital should overlap with the 1s orbital of the second hydrogen atom. Let us see this in the form of a diagram here. I told you that the x-axis and the y-axis, they are perpendicular to each other, right? Let's say this is my x-axis, and this is my y-axis. Okay, we have 2py and 2pz orbitals which have unpaired electrons. So I'll draw the y-axis and the z-axis for you. The y-axis and the z-axis. We know that the y-axis, the z-axis and the x-axis, they are mutually perpendicular to each other. And the shape of the p subshell is dumbbell. So I'll draw a dumbbell along the y-axis. Let me also draw a dumbbell along the z-axis. 2py orbital should overlap with the 1s orbital of hydrogen. So 2py orbital should overlap with the 1s orbital of hydrogen. S orbital, you know, S subshell is spherical in shape, so I'm drawing a sphere here. Again, the 2pz orbital should overlap with 1s orbital of the second hydrogen atom. So the 2pz orbital of nitrogen should overlap with the 1s orbital of the second hydrogen atom. But if that happens, we know that the y-axis and the z-axis, they are mutually perpendicular to each other, so the bond angle has to be 90 degrees. But as per the valence shell electron pair repulsion theory, if the central atom is forming 2 covalent bonds and if it has 2 lone pair of electrons, on the central atom, then the bond angle has to be 104 degrees 31 minutes and not 90 degrees. How do we explain this? Again, this is where hybridization again comes into picture. 2s orbital, 2px orbital, 2py orbital, 2pz orbital, these 4 orbitals, they intermix, and when they intermix we get 4 hybrid orbitals. Why 4 hybrid orbitals? Because 4 orbitals are intermixing, we get 4 hybrid orbitals. What should be the name of those hybrid orbitals? We get the names of the hybrid orbitals from the orbitals that are intermixing. Let me write it down here. So here we have the s orbital, and here we have 1, 2, 3 p orbitals. So we have just one s orbital and then 1, 2, 3 p orbitals that are intermixing. So the name of the hybrid orbitals will be sp3. We get 4 sp3 hybrid orbitals. So this 2s becomes a sp3 hybrid orbital which will have 2 electrons in it. This 2px, it also becomes a sp3 hybrid orbitals. sp3 hybrid orbital. This 2py also becomes a sp3 hybrid orbital. Thus 2pz also becomes a sp3 hybrid orbital. You get to see that the first 2 sp3 hybrid orbitals have 2 electrons each, and the next 2 hybrid orbitals have an unpaired electron. And from the valence bond theory again, we know that if 2 atoms come close to each other, the outermost orbitals having unpaired electrons should overlap. So sp3 hybrid orbital of oxygen should overlap with the 1s orbital of hydrogen, and then again the second sp3 hybrid orbital of oxygen should overlap with the 1s orbital of the second hydrogen atom. So this is what really happens. sp3 hybrid orbital of oxygen, it overlaps with the 1s orbital of hydrogen, and then again the second sp3 hybrid orbital of oxygen overlaps with the 1s orbital of the second hydrogen atom. That is how oxygen is able to form 2 covalent bonds with one each with the 2 hydrogen atoms, right? Since oxygen has 2 unpaired electrons, it can very well form 2 covalent bonds. And how are those 2 covalent bonds forming? The first covalent bond is formed when the sp3 hybrid orbital of oxygen overlaps with the s orbital of hydrogen, the first hydrogen, and the second covalent bond is formed when the sp3 hybrid, the second sp3 hybrid orbital of oxygen overlaps with the 1s orbital of the second hydrogen atom. Now if you see, you get to see that the overlapping orbitals are same. Since overlapping orbitals are same, the bond length and the bond energy of the 2 covalent bonds will be same, and the bond angle will be 104 degrees 31 minutes. These charts have been prepared by Sumaya and Mariam. Video editing is done by Faisal Khan. I'll see you all in the next video. Until then, goodbye.